Hello. Uh, Anybody can confirm my screen is visible?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. Yeah. So before we start, I want to let you know that this presentation is designed for a mixed audience. So we will cover both general ideas and the deep technical details. No matter your background, I hope you learned something new and useful today. Welcome everyone. Today we are discussing design for testing, bridging the gap between simulation and silicon. We will start by exploring exactly what creates this gap and, more importantly, how we can build a bridge across it. Let me also take pen is not okay. So I often think of a brilliant quote from Sherlock Holmes, Arthur Conan Doyle. So it is a capital mistake to theorize before one has data. Insensibly, one begins to twist facts to suit theories instead of theories to suit facts. This is the exact trap we fall into as analog designers. So we easily fall in love with our simulations, but we shouldn't and we never should theorize before we have cold, hard silicon data. My name is Dr. Nithin Thomas Abraham, MTS Analog Design Engineer at GlobalFoundries, and let's get started. A brief introduction about me, already Abhijit covered. Anyway, so I have a academic foundation from NIT Calicut, like PhD, and my core technical expertise spans over power management, data converters and amplifiers, DDICs, GPIOs, and I also worked in advanced technological nodes like 28 nanometer, 22 nanometer, and 12 nanometer. Currently, I work in GlobalFoundries. To understand where we fit in, let's look at this semiconductor pyramid. At the very top, we have the chip foundries or fabs. Next, we have this fabless companies like Google, Microsoft, and Apple. They have brilliant in-house designers, but they don't own fabs. So they reach out to the chip foundries to actually manufacture their designs. Then we have these IDMs, which design their products and have their own in-house fabs to build them. So they don't need chip foundries; they have in-house fabs, but they don't outsource to fabless companies. So they cannot give the designs to the IDMs and fabricate there. So we support these fabless companies, and this entire ecosystem has other material suppliers, EDA software developers, and other. Uh, all these constitute of this semiconductor pyramid. And Global Foundries is one of the leading semiconductor fabs, and we help a huge range of customers who don't have fabs to physically fabricate their designs in our foundry. Let's start the discussion. Let's look at the standard analog design flow and ask a critical question like, is there a fatal flaw in the flow? A quick disclaimer, I am not explaining the entire analog flow today, just the key milestones from design to testing. We start with a month of design on paper, then followed by 2 months of CAD simulation, then another 2 months of floor planning and layout, and then 4 to 6 months of actual silicon fabrication. Finally, after the silicon is out, we spend a couple of months on silicon validation. So I am not sure how many of you are familiar with this analog design flow. So basically, it's a design on circuit, then the schematic simulation, layout, fabrication, and the testing. Uh, I also added the number of months required for each step, and if we count all these months, this is nearly a year from the concept to the test. Now, what is the real challenge? Let's say if we make a fundamental error on day one, we don't find out until day 300 or 300 plus days. That is a massive drain on time, money, and resources. That's why we need to plan for first pass success. So that's the importance of design for testing and thinking about testing at the start of the design. Uh, let's let's ground this on a real example. We will design a circuit till the testing phase, and we will see what are the challenges are. So now here we are designing a load robot regulator. I also don't know how many of you are familiar with a load robot regulator. It's basically a one DC voltage to another DC voltage converter. So we want to take a 1.8 volt supply and step it down to heavily regulated 1.2 volt with less than 1% variation. This is the spec for the design. And the target spec where capacitance 10 pico, load current can seep from 1 milliampere to 100 milliampere, which means this LDO can power a 1.2 volt circuit that can take a load of 1 milliampere to 100 milliampere current output. And we have a quiescent current of 1 milliampere. This is the design current. So this quiescent current, we can use it for the other circuitry required for the LDO. Let's say we have an error amplifier, a bleeding circuit stage. So we only have a 1 milliampere current to all this yeah, for all the design current budget. So the fundamental equation driving this output voltage is V output equal to Vref, which is a Vref given here at the input of the error amplifier times 1 plus R1 by R2. So to pull this off, we need to utilize a single stage error amplifier. Let's say we take it as with a 40 dB or more gain and connected in a negative feedback. So having this high gain is crucial to minimize the offset of the op-amp. So there should be some offset between these two terminals that we need to minimize as low as possible to get a highly accurate output voltage. And like I said earlier, we can use this 1 milliampere current and budget, let's say 10% for error amplifier and 10% for this bleeding current stage. And the rest all load current will take like 1 to 100 milliampere, it will go through the load. And we have a capacitor spec of 10 pico, so we can use an internal load capacitor and we can use an external load current, and VRF also we can connect from externally. So about the working of the circuit, let's say the VRF is 0.6. The error amplifier, since it is connected in a negative feedback, it will try to equalize these two nodes. So this is 0.6 and this voltage will become 0.6. Let's say both R1 and R2 are same resistor, equal resistance. So if this is 0.6, since the current is same, this also will be 0.6 higher than this voltage. So we will get a 1.2 voltage at the output if all works perfectly. So this is the design of paper, which is the first step of our analog design flow. Next, we will move to CAD environment. So we take our paper theories that we designed on paper into the CAD environment. And what we require, we need some AC analysis to verify our 40 dB. Anybody asking anything? Yeah. Okay. We have AC analysis to do the gain. So we said we need a 40 dB gain. We'll use a single stage, not to complicate the design. Then we have the 10 milliampere budget current for this op-amp. So we need to do transient or DC analysis to set this 1 milliampere, 0.1 milliampere current. Then for the LDO, the biggest challenge is to size this transistor. So this single transistor, it should size it very hugely to support the 100 milliampere current spec. And we will also can size the R1 and R2 to set the 0.9 milliampere current. And we will also set the ratio to be equal. So R1 equal to R2, so that we are taking 0.6 and the output will be 1.2. So if both are equal, this is 1 plus 1, 2, 2 times 0.6 is the output. So we ensure this output results with the transient and DC simulation. And we also do stability analysis to check we have a solid gain and phase margin. Because this is a single stage op-amp and we are connecting to the PMOS pass gate. So this will comprise of a two-stage op-amp, both together. So we need to check the phase margin for this, and we will check the stability. And if required, we will compensate the stage also. Then we will see the load and lane regulation. Load regulation means if the output current is changing, the load current is changing, how the V output will change with respect to load variation. And the line regulation is the line voltage or the supply voltage, if it is varying, how output is changing with respect to VDD variation. So these things we do every verification, all the verification we do simulation on a CAD tool like CAD and Virtuoso. synopsis or TAN or some schematic based CAD tool, we can do this. So after this step is completed, all the specs are verified, then we will move to the next stage, which is the layout. So layout, in the layout, precision is everything. So even if you have a perfectly designed schematic, if the layout is bad, the entire circuit will fall. So we employ a common centered matching and for the input pair M1 and M2, and interdigitated matching for the R1 and R2. I will explain exactly why we need this matching in the next slide. So once all the circuit elements are placed, like error amplifier, the cascade, the resistors, the on-chip capacitors are placed, everything is placed, and these are the pads we are adding in the layout, and we connect all the circuit pins to the pads of the pads added in the layout. So this is like a chip level kind of thing. So we have pads also in the layout, and after all these things, we will do post-layout simulation, which is also called PEX, to see how the simulation changes once routing parasitics also are added. Because in the schematic, you don't see some routing parasitics between these two lines or these two lines. So when you are doing the layout, the routing parasitics also come into picture, like R, L, or C. So how that affect our performance of the circuit, that we will get to know in a post-load simulation or PEX. We will discuss the matching in the next slide. Why we need matching? We said we will match these to R1 and R2 and M1 and M2. We will talk more about the R1 and R2 matching. Why we need the matching here? So this is our equation: V out equal to Vref into 1 plus R1 and R2. So look at the resistive divider, these two R1 and R2 divider governing the LDO output. The ratio of the R1 and R2 determines the output voltage. Okay. So during manufacturing, there are different type of gradient that can cause a difference in this R1 and R2. Let's assume don't ignore this gradient direction. Let's assume a gradient direction from purely through the x-axis. So from like 0 to x-axis, there is a gradient. A gradient means there is a difference in resistance. So let's say the yellow resistor have a low resistance and a blue resistor have high resistance. If the gradient is from left to right, it means that uh, R1 is lower and R2 is higher. So this ratio will change, which means it is now no longer 1 plus 1. It will be 1 plus, let's say, 0.9 or 0.8, which will completely change this output voltage. So this can happen in a fabrication. So what we need to do is we need to match these two resistors to make this ratio equal. Okay, so how we can do that? We can do like many ways. One is, this is some kind of common center layout. What we do is, instead of taking a single resistor for R1 and a single unit resistor for R2, we will split this R1 into two parts. So you can see the yellow, and we will split the R2 into two parts. You can see the blue lights. So again, if the gradient is from this direction, so let's say 0 in the x-axis direction, this first yellow resistor will have a very low resistance, and moving towards the x-axis, this last yellow resistor will have a high resistance. So if we connect these two resistors in series, then both of the variations will get compensated, and we will get a mid-value resistance. So this resistor plus this resistor will become a resistance equal to a mid-resistance value. And we also have this blue resistor placed at the center. So if the gradient is in x direction, this will have a slightly low resistor, and this will have a slightly higher resistor comparing these two. And both of these connected together in series, it will give a mid resistance value. Like this way, we can equalize, or we can match these two resistance value R1 and R2. And if you are matching it, we will get exactly 1, and this will equalize the output voltage to exactly 1.2. So this is for the x-axis, but what if we have a y-axis gradient also? So this type of layout is called a common centered layout. So this will uh, cancel all the gradients in x and y direction also. We have like a multiple order common centered arrangements also. But there is a trade-off. how much smaller we should divide the resistance. If you divide the resistor into multiple small units, anyway, we need to connect all these resistors together. So there will be some kind of routing resistance also come into picture that can cause additional mismatch, even if you are matching it in a common centered layout. So it's a trade-off. So how much we should divide, which order we should choose, how much is the routing parasitics, how much symmetrically we can route this resistance. Those things also we need to come. So this is basically matching. This is very much required because of this resistive ratio. One more thing I want to tell about matching is this R1 and R2 does not have to be, let's say we designed this R1 to, let's say, 20K, and this R2 is also 20K because both are equal. We don't need 20K resistance. Let's say both these resistance are reduced to 19K. That is also fine. That does not affect our performance because the ratio of the resistance is more important than the absolute value of the resistance. That's why matching is important. We are not trying to make the resistance value we are not trying to uh, neglect the variation in the resistance value. We are trying to match these two resistors, R1 and R2, to make the ratio equal. So I will skip the slide. This is slightly complicated, but I will keep the slide for you to refer later. Now let's talk about the silent killer, uh, electron migration or EMIR. You can see at the midpoint here. This is basically a metal line. So metal line is routed on top of the silicon. And if the current density is high, where the density is the keyword, the physical force of the electrons will literally move the metal ions over time. So if the current density through this metal line is high enough, then the metal ions itself can move and go to some other location. This can cause breakage, voids, or hillocks. So you can see the metals at this metal layer uh, got moved or pushed to this hillock. So this can cause many problems, many reliability problems and lifespan issues for the circuit. The main issue is it is not visible in simulation. The EM won't show up in standard schematic simulation, but it will destroy our chip's lifespan. One interesting fact is we use this type of technique for one circuit, which is called E-fuse. So in E-fuse, electron migration is like a benefit because we use the same principle electron migration to introduce E-fuse in the silicon. E-fuse is basically a fuse which breaks when it detects a high current density. So we have this simulation tools like Cadence Voltus to see this electron migration specifically. It's not visible in standard simulation, and it will generate a heat map where the current density is more. Based on this, we can decide whether we need to increase the width of the metal lines, or we need to add more wires, or we need to stack the metals to reduce the electron migration. This is like a silent killer because it is not detectable in standard schematic simulation. Another important, equally critical, is the IER drop. Earlier, when I mentioned the specification, I mentioned that we have a 100 milliampere current here, right? So this 100 milliampere current has this path, not from VDD to VSS. The current will go from here to here. Okay. And this 100 milliampere path should have a very low routing resistance. Why? Because let's say our VDD, we are routing the pads. We have this pads of the VDD, and from the pads, we are routing the lines to this transistor source. So let's say we have a routing resistance of 1 ohm. So even a 1 ohm resistor can drop a 100 millivolt drop across this resistor. Thus, not only degrades our performance because you can see our spec is 1.8 plus or minus 90 millivolt. So even this IR drop will have a 100 millivolt drop if the resistance is 1 ohm. That significantly degrades our performance at a low VDD. It also adds a localized heating effect in the circuit that can also cause reliability issues later. But these kind of issues are directly visible in post layout simulation. because these routing parasitics are included in the post extracted netlist. This also we can view through this voltage, cadence voltage, this IR simulations, and we can see similar to this. We will see a heat map like this, and we can see where are the IR drops, where are the localized heating happening, and those things we can see through this same tool. So we did the design. Right, we did the design on paper, simulation verified, then floor planning and layout. We also verified it does not have any EM or IR problems. Then there is silicon fabrication, right? After the layout is completed, we push this layout to fabrication. When we move to fabrication, we are dealing with a physical stack here. You can see the entire stack here. The bottom is the FEOL and the top is the BUL. And if we have packaging, then you have this layer also. Since we are probing from the wafer itself, we have only FEOL and the BOL. So FEOL is basically your transistors. So what you see in the schematic is not actually we are fabricating. So transistors look like this in actuality. So we add different layers through some mask. We do photolithography and those techniques, and we add a metal connection. This BOL is your metal connection from transistor circuit to other circuits, and we tap it from here. We take the output from here. So we can have several wires or something from the transistor, and it will go through the BUL to the top, and we can tap it from here. This is kind of a 3D structure showing the routing and other things. So due to this but you can see this manufacturing will have some kind of manufacturing is not perfect. It can have some kind of variations like diffusion, temperature, etching is also, we are using chemicals, etching won't be perfect. So many kinds of variation can happen. So due to this manufacturing tolerances, transistors don't always become perfect. We characterize this using by process corners. So these are called process corners. So we have this TT, which is called a typical. This is the perfect transistor. If nothing goes wrong, this is the perfect transistor. And we have this FF. FF is basically fast, where we have this NMOS and PMOS, both are very fast. And this is like an extreme corner. And we have this SS also. SS is like both transistors are slow. And we have this skew corners also, like PMOS and NMOS have different. One is slow, one is fast, like this skewed corners also. This shows the extreme corners of the process variations. Like this manufacturing process have lot of variation, and this shows the extreme variations, extreme corners, and the TT is the midpoint of the these variations. But in reality, we can have the circuit in any of the corners, or in between this rhombus like figure also. We can have a circuit with a performance here, here, anywhere inside this rhombus we can have this performance. But these are the extreme critical corners. Above this, if you go beyond this rhombus, then it will be kind of a yield issue. So you can see this simulation results for the loop gain and phase margin. So across different corners, let's say SS, TT, and FF, if you take these three corners, you can see the gain is not same, gain is varying. The phase margin has some variations. Based on the load current, also we have some variations. We have these variations. Uh, 1 second. Yeah. So we have these variations across corners. So what we need to do is, if consider this is a performance metric, we need to make the performance better even if we are manufacturing in any of these corners. So even at SS, FF, TT, we need to meet the specification, we need to meet the performance. That is actually a very critical design job, and that's why it takes like a 1 to 2 months for the simulation and uh, results. So our job is to guarantee that the circuit performance across every single one of these physical manufacturing extremes. So let's take a breath. We designed our circuit on paper, we simulated it on CAD, we did the floor planning and layout, we checked and fixed the electron migration, IR drops, and we even accounted for the extreme process corners during fabrication. So we put in all these efforts, right? So, and the final question is, even if we do all these things perfectly, does our hardware actually match our simulations? That is the critical question. Let's take a wide assumption, like you did a very groundbreaking, like Nobel Prize winning circuit. Okay, so and let's take you designed an op-amp which has 1000 terahertz bandwidth. That is extremely not possible, impossible. But let's assume that we have a design of, let's say, 1000 terahertz bandwidth. The question is, how do you test it? So do you have any equipment in your lab to actually test this bandwidth of your op-amp that you are claiming that you designed and simulated and verified? Without testing, without data, how do you theorize? But so that's the most important thing. We cannot tell that in simulation it is working fine. We should actually test it and show that in silicon that our design is proven, and without the data you cannot do the theorization. You must know the limitation and inaccuracies of your lab equipment before even starting the design. So if you cannot test it, you cannot prove it, even if you have a brilliant design. That's the underlying fact. Yeah, let's come back to this. I will explain this noise measurement aperture. Before that, let's do a case study. This is a current steering deck. I'm not familiar how many of you know, but let's quickly explain how it works. So this current steering DAC is basically digital to analog converter. So we have this digital bits D1, D2 up to Dn. So n is the number of bits. And if you have a digital bits, and we need to convert that to analog voltage using a DAC. So this analog voltage or current. So here we are converting this digital bits to current. Let's assume that a D1 is enabled. The D1 is connected to a switch, and if D1 is enabled or high, and all the others are 0, let's assume one condition. You can see the IOT can have a path, and it can flow through this current mirror, and we will measure the IOT here. So this path IOT will be equal to IU. So whatever IU value of the IU, it will be your IOT. Let's say this is off and only this one is on. Then the IOT will have a path from here to here, which means your IOT equal to 2IU. There is no other path. Let's say if both of these are turned on, the IOT can go to IU as well as 2IU. So this is basically current addition, KCL. So your IOT will be both of them added together, IU plus 2IU, which is 3IU. So based on the digital bits, let's say 0, 0, you will get 0 IU output, 0, 1, you will get IU, 1, 0, you will get 2 IU, 1, 1, you will get 3 IU. So this is basically digital bit to analog current conversion. This is implemented using a current steering DAC. This is the idea behind it. And current steering, you will get alternating IOT plus and IOT minus. In one, IOT plus will be in one direction. Let's say based on the digital bits, it will increase like a ramp, and IOT minus will be like an opposite ramp. So it will be complementary IOT minus and IOT 1. And I think there is a mistake here, like this will be D1 and this will be D1 bar. So this will be opposite of this D1, and both the IOT and IOT minus will be complementary. For the case study, let's assume a 7-bit DAC. 7-bit means your n is n minus 1 is 7. Yeah. Okay. So 2 raised to 7 is basically 128 input combination. 128 input combination you will get from a 7-bit DAC, and let's say you need a 1 megahertz DAC. So your input can vary at a 1 megahertz frequency, and you have 128 input combination, and we are testing like a ramp. So we are varying the digital bits from 0, 0, 0, 0 to 1, 1, 1, 1, and measuring the I output at the 1 megahertz. Okay, this is our design, and we are trying to measure it. So to measure this 1 megahertz, first thing we need to check is the noise component of this measurement. So this is basically aperture, how fast we can measure the output of a node. So what is our frequency? Our frequency is 1 megahertz. 1 megahertz is basically 1 micro. So 1 micro is 1 megahertz, and we need a higher or lower aperture to measure a 1 microsecond time because of the sampling rate. So our aperture time will somewhere in between this 555 nano and 1 micro. And you can see we have this 138 input combination, right? So if you are turning on only one switch at a time, you will get a IU at the output, which is also called 1 LSB, or least significant bit. So let's assume this IU is actually 1 micro. Okay, so 1 micro is my 1 LSB, and 127 micro is my largest digital converted bit. So we have this 1 LSB equal to 1 micro, and if all the digital inputs are 1, then we will have 127 micro ampere current. Let's check the noise level. So we are measuring here at in between 550 nano and 1 micro, and we have this range setting. So this is how we set the equipment to measure which range we need to measure. Let's say we set this at 1 microampere range to measure our 1 LSB current. You can see our noise level is in 1 nanoampere, right? So that is significantly less in comparison to 1 micro. We are well and good. But we cannot measure the next bit. We need a higher current setting to measure a more than 1 microampere current. We have current up to 127 microampere. So we have to force the equipment to a higher range. But if you see, there is no 127 microampere. So we have to set the equipment in this 1 milliampere range. If we are setting it in 100 microampere range, what will happen is at 100 microampere range, the equipment will saturate at 100 microampere. So even if you are measuring 127 microampere, you will only measure 100 micro. You cannot measure 127. So you always need to set the equipment in a higher range. So if you are setting it in 1 milliampere range to measure the 127 microampere, let's look at the chart again. This is the graph, and this is our aperture time. And you can see our noise current is in the level of 1 microampere, which is very close to our LSB current. So that is why we need to understand this before even setting or before even designing the circuit to a 1 microampere spec. Because with this spec, our all low digital bits will see a lot of significant noise, and 127 microampere may see less noise, but all our low digital bits will see a significant amount of noise. So if we know this prior, how we can tune our circuit, how we can rectify this problem. Let's say we have this 100 microampere range. Since we have 127 microampere, that's why we are setting it to 1 milliampere range. So let's assume our highest MSB, like if all the bits are 1, we only have 100 microampere current. Okay, so our largest current is not now 127 microampere. Our largest current is now 100 microampere. At that time, we can set this to 100 microampere range. And 1 LSB will be almost 780 nanoampere, which is not far from this 1 microampere range. Okay, now let's look at the graph again. So this is the graph. So if you say that if you are doing a setting with a 100 microampere range, our noise current will be in 100 nanoampere setting. So that is significantly low in comparison to this 1 microampere noise current. So if we know this prior to our design itself, we can design the stages for max current to set to 100 micro or slightly lower, and we can effectively measure that with our testing equipment without the noise affecting our circuit. So this is one case study we are doing. This is why we need to think about testing before we start the design. Let's get back to our LTO. And before that, I will also introduce this wafer probing. I also don't know how many of you know about this wafer probing station. So if you design a circuit, you taped out in silicon. Then when your silicon is arrived, usually what we do is we need to split this wafers into different square or rectangular pieces. That is called a process called dicing, and then we need to push it to packaging, which we will make it as an IC, and then IC with the pins, and those IC needs to be fit in a PCB. So we need to design the PCB, then we need to connect the IC and solder other components required for the IC in the PCB. Then we need to test it from the PCB pins. That is like a huge process. But here, what we can do is we can measure the circuit from the silicon itself from a wafer probing station. So you can see these probes here. So these probes can be set to touch the pad. Pad I will quickly show again. So you can see we added these pads in the layout, right? So these probes will be uh, put at the top of this pad, or at the almost at the middle of this pads, and these pads are connected to our circuit. So we can measure the circuit directly from the silicon using a wafer prober. You can see this here. So this is basically the tip of the pad, and this entire thing is the uh, tip of the probe, and this entire thing is the pad. I also added links in several slides, so that if you want more info, you can go and check about these things. So you will the test engineer will look through this microscope, and the output of the microscope will be visible here. And based on this output, he will perfectly align the probe to the pads, individual pads, multiple pads. You can see two pads here. There will be multiple pads. So for that, we need a probe card kind of structure. This probe card will have multiple pads, and we can set it to the on top of the silicon and can be measured. So the entire setup is kind of this. We have a chuck, and on top of that the silicon is sitting, and we have this probe card which have multiple probes, and we have this XYZ positioner to adjust the position, and the microscope to manually check the position of the pads and place it. So this is a wafer prober. Yeah. The wafer probing actually saves a huge amount of time, because we don't need to design dice, we don't need to package, don't need to like design the PCB, route, solder, those things. Anyway, all these things we can avoid. This is a huge time saver. Okay, but when we are doing this wafer probing, we need to think about something else also. So this wafer probing introduced like a massive blind spot. It's not a problem for wafer probing, any type of testing. This blind spot we didn't look during the design stage. That is the interface parasitics. So how do we measure our output of this DUT? And are we considering this interface parasitics from the DUT to the measurement or measurement equipment? So these things usually we never consider. We should consider. A good analog engineer considers, but if you are a beginner, we completely ignore this until it is too late. So let's actually trace the actual path from the actual signal path shown in the schematic here. So moving from our device under test on the right all the way back to the lab equipment. So during our simulation, we usually just drop an ideal voltage probe rate on a node and hit run. We run the simulation, but look at the physical reality. First, the silicon hits the bond pad. This is the pad. The pad alone introduces a 1 picofarad capacitor straight to the substrate. Next, the signal travels to the probe card. So this introduces a parasitic inductance of around 10 nanohenry, which is not high for a DC, because LDO, if you are going for a testing, we mostly test in a DC scenario, but this will break your performance for a AC simulation. So this is 10 nanohenry inductor is there. Then we have this contact resistance. Contact resistance is 2 to 20 ohm. This resistance is slightly varying. Why this resistance is varying is because if you see this, where the uh, probe is placed on the pad matters, and how the probe touches the pad also matter. Even a slight angle difference can cause a big resistance difference. So the probe should be very carefully placed on the contact. So that's why this range of resistance 2 to 20 ohms. And we have this 25 picofarad of capacitance just from the probe structure itself. But this is only the probe card. We are in the reached the oscilloscope yet. That signal now has to travel through a 2-meter coaxial cable acting as a 50 ohm transmission line, which adds a massive 200 picofarad capacitance. And this also introduces a significant amount of signal delay. Then it hits the tester on the active differential probe, which has its own input impedance loading the circuit. So when you add all these resistance, inductance, capacitance, just this is just not a single wire, right? It's a complex RLC pass filter connected right onto your output. So this hidden parasite network will degrade your rise time. It will introduce inductor ringing. Then several severely attenuate high frequency signals also due to this inductance and the capacitance, of course. The waveforms you finally see on your oscilloscope screen. This is the oscilloscope screen. We will see the waveforms. This is the cable that I was talking about. Oscilloscope screen is actually a signal that has battled its way through all these parasitic obstacle codes. So what we need to do is we need to understand this parasitics at the design level itself, and we need to model it, and we need to introduce this in our CAD simulation. That will be completely blind to what silicon is actually doing on the bench if you don't do this at all. So this is another thing that we missed during the design phase. What what is the actual cost? Let's take one example. Let's quantify this disaster. Okay. So we optimized our layout for this 100 milliampere path, right? So we reduce the resistance very low that it won't drop any significant IR drop across this line. But you can also see a resistor here, which is introduced from the probe card, this R probe, which ranges from 2 to 20 ohm. So this resistor is connected to the output, right? So we have this internal voltage and we have this measurement circuit measurement probe. So there is a difference between the internal voltage and the output voltage due to this resistance and this huge current flow. Okay. So best case scenario, let's take 2 ohms, right? 2 ohms. 2 ohms and 100 milliampere, it means a 200 millivolt drop. So our perfect 1.2 volt internal output reads as a 1 volt pad at the output. So if even if this is 1.2 volt exactly, we designed it very accurately, and the layout is done also perfectly. This is 1.2 volt exactly, but due to this probe card resistance and this high 100 milliampere load current, we will see a 1 volt only instead of 1.2 volt due to the resistance drop. What about the worst case scenario? Let's say this resistance is not 2 ohm and this is 20 ohm. 20 ohm into 100 milliampere, it's 2 volt. Our supply is only 1.8 volt, which means we measure absolutely nothing, and it's 0 volts, it's nothing. This is the importance, or this is why we have to design with the testing in mind. So if we know this prior, how we can solve this? We can solve this like in many ways. So we reduced this resistance from the layout, right? So how about we reduce this resistance also? But the minimum resistance is 2 ohms, right? How can we reduce this? One way of reducing this resistance is connect multiple probe to this pad. So if we connect multiple probes, what will happen? The resistance will become parallel, and you can see the resistance division happening, and you can bring down the resistance to zero 0.5 ohm or zero 0.2 ohm or less. So this will minimize your voltage drop through this path. That is one way. But to connect the multiple probes to a pad requires a large pad area. So again, I will go back to the layout. So you can see this pad area. After fabrication, we cannot do anything, right? This is already fixed in pad. So if you want to connect multiple number of probes, we need to set a large pad in the layout so that multiple probes can be placed perfectly in the pad. So this pad size can be increased. That facilitates multiple probe placement, and we can reduce the series resistance. That is one approach. Another way is it's very simple. Instead of connecting a single pad to the output voltage, we can connect it two pads. So we can connect two pads to the output voltage. So one pad we can give this iLoad current, 100 milliampere current, and the one pad we will keep it. We will not give any current, or we can force a zero current, and we can measure a voltage here. So one pad can be used to measure the voltage, which is a voltage sensing pad, and one pad is to apply the load current. So in that way, you completely eliminate the flow of this 100 milliampere through this R probe resistor when we are measuring the voltage. So that is another way of doing it. This will completely eliminates the R probe from the equation. So we can directly take. But here also we need two pads for the V output. We need to think ahead of this before the testing, right? We need to at least think about this two pad connection in the layout stage itself. So this is another thing. Now let's talk about this power supply integrity. Okay. Think about the complete routing path. Okay. From your lab power supply through the cable, through the probe card, through the probe needle, then through the pads in the layout, then through the layout routing, then you reach the final circuit. So you will have a very long path from your supply to your circuit. So this very long path have like inherent inductance. And when our circuit demands a sudden transient current, this inductance fights the change, causing this voltage, the VDD of the actual circuit to drop. How we can remove this effect? So because of this very long routing, right? So what we do is, to prevent this, we can actually place a capacitor very close to our circuit inside the layout itself, inside very close to our circuit itself, to supply the current required for the sudden transitions happening for the circuit. So if some sudden transitions are happening at the output, the circuit does not need to fetch the current from the main supply. This capacitor is already charged and it can locally provide the current to the circuit. These are called decaps or decoupling capacitors. This is a common method we use to uh, nullify this long path problem. This is like similar to a water supply tank. Like, so you have like a main city supply and a distribution pipe that is very long, and you have this local water storage on top of your house or inside your house somewhere, and from there you are getting the supply, right? So if you are taking this water directly from the city supply, so when multiple people are using this water at the same time, a sudden pressure can drop and you won't get any water at all. So at a high demand condition, it's a problem. That's why you need a local water supply to supply for your uh, sudden needs of water. So that is the same thing what the decoupling caps do. So we can add a decaps inside this layout. Next point I want to talk about is the ESD. We surveyed all these things, and now we must survey electrostatic discharge also, ESD. ESD is a big problem. It's this is basically happening due to the handling of the device, how we are handling the device. So even a human, you can see this graph. HBM is human body model. So human body model is modeled in this graph, and the CDM is chart device model. The based on the human bodied model, a human touch can cause a voltage difference of 2000 volts. So consider applying a 2000 volts to a 1.8 volt supply. So this will directly damage your device. So there is nothing for us to test. So we should carefully handle these things in our lab. That is one thing. Another type of model is the CDM, which is the charge device model. When we use machines to test this, if you use a prober or probing wafers or pins or contacts, so these contacts also can be charged. That device can be charged previously, and there will be a huge rush of current. So this current can have like a 5 ampere is here it is model 5 ampere, but there are other higher currents also. It can go up to 10 or 14 amps current can flow at a very short duration through our circuit. So if there is no current path, if our circuit is not connected at all, there should not be a current path at all, right? So if there is no current path, the current will force through the circuit and break all the devices. So this is ESD. This is very it causes a lot of problems during testing time. We should carefully test, and testing always should be done in a very controlled environment. That is one thing. But in circuit, how can we protect this? There are ESD protection devices which we can add to the circuit. So this is our internal circuit to protect the single gate or a thin gate. We can add ESD protection devices at the input pad itself, so that any sap happening will bypass through this diode and flow through this path to prevent any path to the internal circuit through the gate. So it will provide a path for the current or voltage to conduct. If it is a positive sap, it will go like this, and negative sap, it will go like this. And similarly, we can protect the output pad with the buffers and other protection diodes also. And this is called a clamp. So if there is like a huge current at this voltage at this VDD or current, then this current can directly couple to the gate of this NMOS, and this device can turn on. But this will still be zero because of this RC delay, and this will bypass the short the VDD and VSS to provide a current path from VDD to VSS, and this will not allow the current to flow through our internal circuit breaking circuits. So it will provide a path through this device which have a high breakdown voltage. So these type of clamps and diode protections are very essential in the uh, circuit or layout itself to protect from this waste. That is another thing. We are almost at the conclusion level. So the hard truth is nothing is ideal. So this is a oscilloscope waveform of a perfect DC. Okay, you can see nothing is perfect, nothing is ideal. Simulators feed us like a perfect DC lines, right? And we have like a very good digital clocks. What are the simulation settings for a clock? We have this pulse width, the rise time, fall time, and the voltage peak to peak. That's all. We do this in our simulation CAD environment. But what is the real scenario in real life? What is the case? It's not an ideal. It is jagged with noises. The clocks are not ideal. There will be skew, there will be jitter, there will be ringing due to RLC load, there will be monotonicity. Then slew rate can differ, rise time and fall time can differ. This peak won't even may reach the highest value. There can be overshoot which can damage our circuit. There can be undershoot which goes to negative voltages, which can also cause noises, substrate noises, or it can also cause damage to our circuit. So all these things we need to consider. That's the importance of adding the prop card model or the prop parasitics also in the simulation, and to test what are the effects, how our performance is degrading, any blind spot we have. These things we need to see. So we go back to the drawing board, back to the paper design. We designed this at the first slide, right? So this was the first phase. So knowing everything we know now, what changes will you make in your design choices? First thing which I didn't cover is the output capacitor, which is already part of the circuit. This is 10 pico, which we added in the layout, which we do not require at all, right? So we go back to our pad. This pad itself has a 1 picofarad capacitor and the probe is 25. If we are connecting to a cable for the oscilloscope measurement, it will be 200 pico. So at least we will have 26 pico at the output. So there is no need to connect this 10 picofarad at all in the layout. To set a minimum capacitance, we can connect like a 1 picofarad in the layout, but not 10 all 10 pico is not required at all. That is one thing. It will load the circuit unnecessarily. Next thing, what changes you will do? We already discussed the two pad strategy to sense the voltage differently and to apply the current load to a different pad to minimize the difference between the voltage sensing, the output we are measuring and the internal voltage. Then we discussed about this matching techniques that anyway we are doing. And what else? The main thing we need to think about in a circuit and testing perspective is what are the connections to the external world. So you can see we have a connection of VDD or the pins, you can simply say, or pads. These pads are acting as a gateway from external world to your internal circuit. Can it corrupt your device performance, or can it carry some kind of noise? Can it give a sap to the circuit? Do we need to add protection circuit to those pads? Antenna diode considerations are there. So all these things we need to analyze. Let's take about this pin VRF. VRF is connected to external world. We decided on the earlier design choices, we can supply an external voltage at the VRF, right? And look at this equation, V output equal to VRF into 1 plus R1 by R2. If we have some kind of noise at the VRF, this can directly couple to this output, right? Because our equation is V output equal to VRF into 1 plus R1 by R2. So did we consider this in our design? Because so that is the important point we need to consider is what are the pads that is connected to the external world and how our circuit performance can degrade. So this is one point of noise entry. Next is this VDD. We already discussed there is a lot of transient noise that can come from VDD. And this VDD also directly coupled to the output through this basket. So any noise at the VDD can cause a VGS change, and this can also change the current or the output voltage. So this is also another noise coupling path. So what we missed in the simulation is called a PSRR simulation, or power supply rejection ratio. So how much the noise from the power supply we can reject at the output. So that is also an important spec for the LDO. This also we need to consider. Then there are other things like a ground bounds, other things you can search internet. So during the design on paper, you understood, right? Why we need to consider designing testing at the first itself for our design to work, or if you want to prove our design in the testing phase, we need to think about from day one. And one thing I want to point out is this is just a pure analog circuit. Okay, so this analog, why I take it is fairly simple to explain, and it does not have much complication during testing because it's basically a DC testing. But if we go to a mixed signal testing where we have multiple clocks, we may have uh, some variation, some noise requirements also. So it's in a mixed signal design, this will become more complicated. So we may need to scratch our heads more, and we need to absolutely think about the testing before even starting our design on paper. And there are many layout strategies also to mitigate these problems, to reduce the coupling cap. Then there is GSG routing, that we shield the signals between grounds. Many layout techniques are there during the mixed signal, but you get the gist of the idea what I was explaining. So I want to leave you where we started with this code. So it's a capital mistake to theorize before one has data. As engineers, we easily fall in love with our simulation and its results. If our simulation results are perfect, it looks good, we completely or blindly trust those results. But when the silicon comes back and the data doesn't match, the temptation is to make excuses to twist the real world facts to fit our perfect theories, right? So that is not true. That is not right. A true unlock mastery isn't just about finishing a schematic. It's about shifting your mindset. If you design from if you design for testing from day one, we stop fighting the hardware and start working with it. And I'm ending this presentation. Thank you.